Let's now take a look at two other representations of a line in space that we can get from these generic parametric equations. If you think about it in terms of a vector, you could represent x, y, and z. So suppose you think of x, y, and z as a vector, and then x naught, y naught, and z naught, suppose you think of that as a vector, plus t times a, the vector with components a, b, c. You could represent the parametric equations as a vector equation like so. Do you believe that? I mean, think about it. If you can get, just look at the x. So we're saying x would be equal to, if you actually did the multiplication and then the addition here, you'd get x naught plus at, right? So you'd get x is equal to x naught plus at, and you could do the same thing for the other ones. So this would be a vector equation, a single vector equation of the line. We can't represent the line using a single equation in space like we can in the plane, but we can use a single vector equation of the line. So that might come up, so be aware that some books write it that way. And then there's also the symmetric equations you get if you solve these parametric equations for t. So imagine subtracting x naught from both sides, dividing by a. If you do that for each one of these, subtracting y naught from both sides, dividing by b, subtracting z naught from both sides, dividing by c, you'll get the symmetric equations of the line, and they're all equal to t. So the symmetric equations turn out to look like this. T equals x minus x naught over a, which equals y minus y naught over b, which equals z minus z naught over c. These are called the symmetric equations of the line. I won't refer to these that much in this class, maybe in one or two homework problems, and then never again. But it might come up in another class, so I mention it here. Let's go ahead and find the symmetric equations associated with these parametric equations that we found in that last example. What you do is just solve each one of these for t. Solve each one for t. So if you solve this one for t, what do you get? You get t equals x plus 2 divided by 2. What do you get here when you solve for t? Y over 4, right? What do you get here when you solve for t? Z minus 4 over negative 2. And so the symmetric equations then are x plus 2 over 2 equals, they're all equal to t, so they're equal to each other, so that equals y over 4, which equals z minus 4 over negative 2. Okay?